Hello guys, hope you have been having a very lovely day. In this video, let us learn about how to calculate flux linkages within the conductor. So before we actually delve into the topic, let us see why we actually need line parameters. Line, that is L-I-N-E. There are a few things called line parameters, which is your inductance, capacitance, resistance, shunt conductance. So these are your line parameters. So to build or to make a proper transmission line, it is necessary that we calculate all the line parameters properly. Only then we'll be able to make a successful power system network. So the first thing we are going to deal with is inductance. So for calculating the inductance, we need to calculate flux of a conductor. Now flux in any current carrying conductor can be out of different ways. The flux can be due to its own, can be due to a point in its own, or it can be due to an external conductor. There are many methods again, but in the first video let us learn about the flux linkages within the conductor. So this is the first one, in which we talk about inside the conductor. Okay, for that I need you to focus on this. This is a conductor. Now I am assuming this distance to be r, and what I am assuming is at a distance of x, I'm just drawing a circle with radius x. This is what I'm interested in, and I'm considering another small element dx. Okay, and a small length dl. All this can be told later, but I just want you to consider this in the beginning itself. Now, first thing, when you want inductance, think about what you need to calculate. You need to know the flux linkages. If you need to know the flux linkages, you need the flux density. If you need to know the flux density, you need to know the magnetic field intensity. Now, at this small differential length, I'm going to calculate the magnetic field intensity. Hx. Now, as you all know that Hx is equal to closed integral of Hx, the differential length dl is equal to Ix. We all know this. I'm assuming this, see, this radius is x and this is the referential small element L, and here I'm calculating the magnetic field intensity Hx. Now we all know from this, we know that. Now dl is something here. So if I'm integrating it, it is a closed integral. So if I'm integrating dl, what I'm going to get is Hx 2 pi x is equal to I or Ix. Now, what if I need just the value of Hx? I'm going to write it Ix by 2 pi x. So Hx is equal to Ix by 2 pi x. This is the first thing you need to remember. We are done with that. Now, the next thing you need to calculate is, consider this whole conductor. There is a current passing in it, and consider the smaller part of radius x and of radius r. So the smaller part of radius x, even that part carries a current, and the current carried in this part and the whole conductor is different. So Ix, which is the current we have assumed here, if you notice, is different from the entire current in the conductor I. So we know that the current that flows is directly proportional to the cross-sectional area. So the area of this is pi x square of Ix. Whatever circle carries Ix, the cross-sectional area is pi x square. And for I, it's pi r square. So pi and pi go away, and we have Ix is equal to x square by r square into I. So now we have another equation. Ix is equal to x square by r square into I. Now we substitute the value of Ix in Hx. So Hx is equal to x square by r square into I into Ix by 2 pi x, which is equal to, wait a minute, we substituted Ix, I'm sorry. So yeah, which is equal to x square by r square into I by 2 pi x. So what we get is x by 2 pi r square I. Okay, so we have Hx is equal to xi by 2 pi r square. So now remember, it is ampere turn per meter magnetic field intensity. So we have the value Hx, which is equal to Ix or Xi by 2 pi r square. Now we need to further calculate, what we need to calculate further is the magnetic field density Bx. We know that Bx is equal to mu Hx, where mu is equal to mu naught mu r. But however, for this step, we'll just have mu into Hx. So this is equal to mu into remember the value of Hx from this? Xi by 2 pi r square. Xi by 2 pi r square. So this is the value of Bx, and the units are Weber per meter square. Okay, now what we are interested in is the flux linkages are our next interest. Now look at this diagram again. We are considering a small tubular element. We have this radius x and a very small tubular element dx. Consider dx. So now if I want the flux per meter length, okay, it goes like this. This is d phi is equal to mu Ix by 2 pi r square into dx Weber per meter. So these are just take care of the units, see what the different units we are using, and just have a look. See, we have Bx. We need to find out for the small tubular element dx the flux linkages, and so we have d phi is equal to mu Ix by 2 pi r square dx Weber per meter. So this is the flux per meter length. Now we know that the flux linkage, which is what we want. You know what a flux linkage is. Now the surface area multiplied with so and so stuff. Now the flux line what we are talking about is at x. So now 0 is less than x less than r, isn't it? Yes. So this total current, which is I, this flux links with just a part of the current, as we have already talked here about this expression. It links with only a part of the current, and that part of the current is pi x square by pi r square. So this part of the current is just dealt in our flux line, by our flux line. So the flux linkage, for d phi, what we have talked about before here, d5, only for d5 is given by d psi is equal to pi x square by pi r square into d phi. Okay, you know the value of d phi. What is the value of d phi? Substitute it. So d psi is equal to pi x square, pi and pi goes off, so x square by r square into d phi. Substitute the values. Mu I x by 2 pi r square dx. Okay, so this is your flux linkage for that particular spot. Now we have mu I x cube by 2 pi r power 4 dx Weber turn per meter. So this is d psi. But is this enough? We are supposed to calculate it for the whole conductor. Now you can tell it easily. What is the radius? It starts from 0, ends at r. So just integrate it your way. So now internal flux linkage. which is which is the total of all the flux linkages. Now this is integral t psi d psi 0 to r. The radius is r, right? So now we have mu I by 2 pi r power 4 into x power 3 plus 1 is 4 by 4. So this becomes r. Yeah. So r power 4 and r power 4 go away, and we have mu I by 8 pi. So this is the actual internal flux linkages. So this is actually the total of all the internal flux linkages. But since we can go further than this by considering that our conductor is non-magnetic, in which case we know our mu, which we just ignored here. We know our mu is mu naught into mu r, right? So mu r is equal to 1 for a non-magnetic material, and mu is equal to mu naught is equal to 4 pi into 10 power minus 7 Henry per meter. So by substituting this value in this, we can get psi internal is equal to 0.5 I into 10 power minus 7 Weber turn per meter. So that is the final value what we can get for the total of the internal flux linkages in the conductor. Now you can also go further and find out the actual internal inductance in the conductor by just writing by I. So by just dividing whatever flux linkages, the total of flux linkages you have got by I, you can find out the inductance of the internal inductance of the line. So just a brief brush up of what we have learnt. We have a conductor of radius r. I am considering at a distance x from the center a tubular surface, a tubular section, don't think of a surface, and I am finding out the magnetic field intensity Hx at that point, and the differential length is dl. So dl is actually a small part on the circle of the radius x. So in calculating h of x, I say integral of hx dl, which is the differential length, is ix. Now what we know is dl is a small element on this circle of radius x. So since it is a closed integral, dl becomes 2 pi x. So hx 2 pi x is equal to ix, and we have hx value. Now keeping this value aside, we know that the current passing through a conductor is directly proportional to the area of the cross section. So we have ix by I is equal to pi x square by pi r square. So we have the value of ix in terms of the actual current passing in the conductor. So ix is equal to x square by r square into I. Substitute this value of ix in hx. Now we have hx is equal to ix by 2 pi r square ampere turns per meter. So this is what we have. Now we continue by calculating the magnetic flux density Bx, which is equal to mu into Hx. Just substitute the value of Hx in Bx. After getting that, consider a small tubular element dx. For that, you get the flux per meter d phi is equal to so and so. Now we know that the flux line which we are taking, it links with only part of the current, and that part of the current is given by pi. This radius is r and this radius is x. So it only links with pi x square by pi r square, part of the total current. So now don't look at the top, let's start looking from here. So d psi is equal to pi x square by pi r square into d phi, which is, you know the value of d phi, so just substitute the value of d phi in this equation and then simplify it and you get d psi. Now integrate d psi to get the total of the flux linkages in the conductor, internal, remember. After getting the total internal flux linkages, you can substitute mu r is equal to 1 since our conductor is of a non-magnetic material, and by taking mu is equal to 4.10 power minus 7 Henry per meter, you can calculate internal flux as this. And you can also calculate inductance from this internal flux linkages by just dividing the total of internal flux linkages by I. So this is how you calculate flux linkages within a conductor. Hope you found this informative and useful. Thank you and have a lovely day ahead.